What if the most important discovery in our solar system is not a monument, a signal, or a face staring back at us from the dark, but a quieter truth that life may prefer the hidden places? For generations, we imagined alien life as something dramatic, a transmission from the stars, a ship crossing the night, a civilization announcing itself in symbols we could barely understand. But science has led us somewhere more intimate and perhaps more humbling. Again and again, the evidence points not towards spectacle, but toward water, chemistry, warmth, and time. Towards small shelters, carved beneath ice, inside rock, under clouds, far from sunlight, and beyond the reach of easy wonder. In our own world, life began in obscurity. It took hold in deep oceans, in mineral-rich vents, in places no human eye would ever see for billions of years. So it may be a very human mistake to expect life elsewhere to appear in forms that are obvious, luminous, and easy to recognize. The universe does not owe us clarity. It offers hints, fragments, and conditions. We are left to interpret them. This journey is not really about proving that we are not alone. It is about standing at the edge of uncertainty with honesty, about visiting worlds once dismissed as dead, frozen, poisoned, or silent, and asking whether those judgments were too confident. In the cold belt of asteroids, beneath the cracked shells of distant moons, inside buried oceans and acidic skies, there may be habitats we overlooked simply because they did not resemble home. So the question is no longer only whether life exists elsewhere. The deeper question is whether we have understood life itself, how resilient it is, how patient, how willing to endure in darkness until someone, somewhere, learns how to look. What if the first refuge for life is not a planet at all, but a wounded stone drifting in silence between worlds? In the asteroid belt, where sunlight thins and distances begin to feel abstract, Ceres moves with the quiet dignity of something long overlooked. For centuries, it was filed away as a leftover, a dwarf planet too small to matter, too cold to inspire much hope. Then a spacecraft arrived and found light where there should have been only darkness. The bright patches on Ceres did not shimmer like city lights or signal mirrors. They were stranger than that. They were deposits of salt, brilliant against the soot-colored ground, clustered inside impact scars like memories the surface had failed to bury. From orbit, they looked almost intentional, as if the little world had cracked open just enough to reveal a secret. Scientists traced those luminous marks to sodium-rich minerals left behind by briny water. Not fantasy, not spectacle, chemistry. The sort of chemistry that suggests an inner life beneath a barren face. Somehow, in a body barely large enough to hold our imagination, water had lingered underground and mingled with rock, creating the kind of mineral-rich environment that on Earth often accompanies heat, motion, and possibility. That alone would have been enough to change the story. But Ceres offered something more unsettling. Signs that it may not be finished. A faint haze, a suggestion of vapor, hints that even now, beneath crust and crater, pockets of salty liquid may still persist in the cold. Not an ocean in the grand cinematic sense, but reservoirs, veins, hidden chambers where time moves slowly and chemistry keeps its patient watch. It is a humbling thought. We tend to search for life in the obvious places, under generous suns and broad skies. Ceres proposes another model entirely. It suggests that habitability may not belong only to the majestic. Sometimes the conditions for life survive in small, battered worlds that should have gone silent long ago. And if a body this modest can keep water in the dark, then perhaps the universe is less empty than our first impressions would have us believe. What if one of the most promising places for life in our solar system is a world we once assumed was far too cold to matter? Europa does not welcome the eye. It is a moon of pale fractures and bruised lines, its surface sealed in ice so bright it seems almost sterile. From a distance, it looks less like a living world than a frozen relic, something preserved rather than active. And yet, the deeper scientists looked, the less Europa resembled a tomb, and the more it began to resemble a locked door. Beneath that frozen shell, evidence points toward a global ocean, not a lake, not a buried pocket. An ocean vast enough to contain more water than all of Earth's seas combined. Tides from Jupiter's immense gravity knead the moon from within, creating friction and heat, turning orbital stress into energy. In other words, Europa may possess three ingredients that matter profoundly in the story of life: liquid water, chemistry, and a source of internal warmth. The ice above it is not smooth or eternal. It shifts, cracks, drifts, and reforms. In some places, the surface appears to have broken apart and refrozen, as if the moon has been quietly rearranging itself over ages beyond memory. There are also signs that material from below may sometimes rise upward, and that the surface, in turn, may carry oxidants downward. If that exchange is real, then Europa is not only wet, it is dynamic, it is circulating. It is, in a planetary sense, breathing. No one has seen what lies in that ocean. There may be darkness without end, mineral chimneys, or nothing more than cold water and stone. But on Earth, life learned very early how to thrive in black oceans without sunlight, drawing energy from chemistry instead of day. That memory shadows every question we ask about Europa. Perhaps the true mystery is not whether life could survive there, but whether we are prepared for how simple and ancient it might be. Not empires, not voices, just persistence, hidden under ice, waiting in a sea no human being has ever touched. What if the clearest invitation to look for life beyond Earth is not hidden at all, but rising into space in a plume of ice? Enceladus is small enough to be underestimated. A white moon circling Saturn, bright as fresh snow, no wider than some countries are long. By all the old rules, it should have grown cold and inert ages ago, another frozen object preserved in silence. And yet, when Cassini drew near, it found the opposite of silence. It found motion. It found breath. From fractures near the moon's south pole, enormous geysers were erupting into the black. Water vapor, ice grains, salts, and carbon-rich compounds streamed outward with such force that they helped feed one of Saturn's rings. This was not a rumor inferred from distant light. It was material from the interior, thrown into space as if the moon itself had opened a window and let us sample its hidden depths. The deeper revelation came later, when the chemistry of those plumes began to tell a story. There were signs of organic molecules. There were tiny particles consistent with hot water interacting with rock. And there was hydrogen, the kind that on Earth often appears where seawater meets warm mineral interiors, creating chemical gradients powerful enough to support life without any sunlight at all. In that moment, Enceladus changed from a curiosity into something far more intimate, an ocean world with active hydrothermal systems still working now. This matters because life, at least as we understand it, does not begin with comfort. It begins with opportunity. A solvent, a source of energy, a setting where chemistry can become metabolism and persistence can become inheritance. Enceladus appears to offer all three, not in theory alone, but in active exchange, with its underground ocean sending evidence into space for anyone patient enough to notice. It is hard not to feel a quiet astonishment here. On a moon once dismissed as too small, too cold, too remote, nature may have assembled the same conditions that once shaped the earliest living systems on Earth. So the question lingers with unusual force. If a hidden sea can speak through ice, what else in the solar system has been speaking softly all along, waiting for us to learn its language? What if one of the strangest places in the solar system is not mysterious because it is hidden, but because it is visible in plain sight? Iapetus turns slowly in the far reaches of Saturn's domain, carrying on its surface a puzzle that seems almost too deliberate to be natural. Across its equator runs a ridge so long and so precise that it looks, at first glance, like a seam left behind by some forgotten act of construction. It stretches for more than 1,000 kilometers, rising sharply above the surrounding terrain, thin in places, monumental in others, as though the moon had once been stitched together and never fully healed. There is, of course, no evidence of engineers here, only geology, time, and the difficult honesty of not yet knowing. Scientists have proposed that Iapetus may once have worn a ring of debris around itself, and that over immense ages this material drifted inward and collapsed along the equator. Others have imagined ancient tectonic forces, or the slow freezing and reshaping of an early shell. Each idea offers part of a path. None explains everything with complete comfort. And then there is the moon's split personality. One hemisphere is dark, absorbing light like coal dust. The other is bright, reflective, almost wintry in its clarity. The ridge appears most strongly in the darker terrain, which gives the whole world an uncanny character, as though different histories had settled onto the same body and never fully merged. Iapetus does not simply look old, it looks divided. That may be why it lingers so powerfully in the imagination, not because it proves anything extraordinary, but because it reminds us how quickly the mind tries to turn uncertainty into narrative. Faced with something unusually exact, we reach for intention. Faced with an unexplained form, we want authorship. Yet nature has always been capable of shapes that feel designed, even when they are born from chaos. So Iapetus leaves us with a quieter lesson. The universe does not always hide its enigmas in darkness. Sometimes it places them in full view, under open light, and asks whether we can live for a while without an answer. What if life does not need a surface at all? What if an entire world can hide its most important possibilities underneath a shell that never opens? Ganymede, the largest moon in the solar system, does not announce itself with geysers or glaring brightness. It carries a more subdued kind of mystery. Its face is ancient and scarred, marked by impact and ice, a record of endurance rather than drama. Yet beneath that old exterior may lie something astonishing, not a buried sea alone, but a layered interior of oceans trapped between sheets of ice, stacked in darkness like chapters no one has read. For a long time, size was part of the intrigue. Ganymede is larger than Mercury, a moon grand enough to feel almost planet-like, but scale by itself means little. What changed the conversation were measurements of its magnetic field and the subtle clues they offered about conductivity below the surface. The evidence suggested salty liquid water, deep underground, shielded from vacuum, radiation, and the blunt violence of space. That hidden ocean may sit far beneath the crust, pressed between different forms of ice created by immense pressure. It is a strange image. Water not under open sky, but enclosed on both sides, as if the moon had folded the possibility of life inward and sealed it away. Even more remarkable, Ganymede has its own magnetic field, a rare feature among moons, creating a complicated interaction with Jupiter's powerful magnetosphere. In that invisible tension, the world becomes more than a frozen satellite. It becomes active, electrically alive, engaged in forces larger than itself. Would such a deep, isolated ocean be habitable? No one knows. Perhaps the pressures are too high, the chemistry too limited, the energy too scarce. Or perhaps life, if it begins at all, asks less of a world than we once believed. On Earth, organisms have survived inside rock, beneath oceans, in darkness and under crushing extremes. Again and again, biology has humbled our assumptions. Ganymede offers no easy romance. Its promise is distant, buried, and hard to reach. But that may be exactly why it matters. It reminds us that the search for life is not only a search for visible beauty, it is also a search for hidden endurance, for quiet systems working out of sight, for worlds whose deepest truths never rise to the surface. What if the most Earth-like hope in the solar system is also one of the loneliest landscapes we have ever touched? Mars has always occupied a special place in the human imagination. It glows in the night sky with a familiarity that invites projection. Ancient people saw omens there. Modern people saw canals, civilizations, and a second chance for life to bloom under another sun. The truth, when it arrived through orbiters, landers, and rovers, was quieter and more complicated. Mars was not a mirror of Earth. It was a world of loss. Yet loss can leave evidence. Across its surface lie dry river valleys, mineral deposits shaped by water, lake beds fossilized in dust, and rocks that remember long contact with liquid. Billions of years ago, Mars was not the frozen desert we know now. It had flowing water, a thicker atmosphere, changing seasons, and environments that may once have been habitable. In places like Jezero crater and Gale crater, the ground still carries the chemistry of those vanished waters, like handwriting no wind has fully erased. That is why Mars remains so compelling. Not because it looks alive now, but because it may have been alive once, when the planet was warmer and more forgiving. If microbes ever emerged there, they might have left traces in ancient sediments, hidden biosignatures in clay, salt, or stone. Or perhaps, as the surface grew hostile, some life retreated underground, following moisture into the subsurface where radiation could not easily reach. The planet we see today is austere. Its air is thin. Its cold is severe. Dust moves across empty plains where rivers once traveled. And still, it refuses to close the case. Methane has been reported in puzzling bursts. Brines may occasionally form under rare conditions. Beneath the regolith, ice remains. Mars is not a dead question. It is an unfinished sentence. Perhaps that is why it holds us so deeply. Mars is not only about alien life, it is about fragility, about how a world can change, how habitability can fade, and how the memory of water can outlast the water itself. In that red silence, we are not only looking for another biology, we are looking at a possible version of impermanence and asking how long life can hold on when a world begins to forget how to welcome it. What if Mars did not lose life all at once? What if, as the planet hardened into cold and rust, a final remnant slipped underground and kept going in the dark? Beneath the south polar ice of Mars, radar signals have hinted at something difficult to imagine on such a frozen world. Bodies of liquid water buried far below the surface. Not open lakes in any earthly sense, but dense, bitter reservoirs sealed under layers of ice and frozen carbon dioxide. preserved in a realm where temperatures fall so low that ordinary water should be impossible. And yet, impossibility has a way of softening when salt enters the story. These hidden waters, if they are truly there, are thought to be brines so concentrated that they resist freezing even in the Martian cold. They would be harsh beyond comfort, loaded with chemicals, lightless, pressurized, and profoundly isolated. To most forms of life on Earth, such places would seem less like habitats than punishments. But Earth has taught us caution before declaring any niche uninhabitable. Microbes have endured in Antarctic brines, in deep subsurface fractures, in salt pools that appear almost designed to exclude life. Survival, it turns out, can look far stranger than our first definitions allowed. That is what makes these Martian hints so compelling. They suggest not a thriving biosphere, but the possibility of a refuge, a last interior shelter for organisms that may have emerged when Mars was younger and wetter, then retreated downward as the surface surrendered to radiation, thin air, and time. In that vision, the planet did not simply die, it withdrew. Its remaining water became hidden, its chemistry more severe, its potential for life reduced but not erased. There is something deeply human in that image. We understand endurance in diminished conditions. We understand what it means to persist after abundance has passed. Mars, in this sense, begins to feel less like a foreign planet and more like a memory of resilience written in geology. And so the question changes once again. Perhaps the search for life is not only a search for beginnings. Perhaps it is also a search for what remains when a world grows old, and whether even then, in buried salt and darkness, something still chooses to endure. What if one of the best places to search for life is not a world that resembles Earth, but one that rewrote the rules of what a living planet might look like? Titan drifts through Saturn's realm, wrapped in a thick orange haze, a moon so veiled that for years it seemed more atmosphere than place. Beneath those clouds lies a landscape both familiar and profoundly alien. There are rivers, lakes, rain, shorelines, and seasons. But the liquid moving through this world is not water. It is methane and ethane flowing across a crust of water ice as hard as stone in the bitter cold. At first, Titan seems too strange for biology. The temperatures are so low that water behaves like rock, and the chemistry on the surface unfolds at a pace that feels almost suspended. Yet that same chemistry is precisely what has made Titan irresistible to scientists. Sunlight and Saturn's radiation drive reactions in the upper atmosphere, creating a rich stew of organic molecules that drift downward and settle onto the surface. In other words, Titan is full of the raw ingredients that, under the right conditions, can become more complicated than anyone expects. And then there is what may lie below. Many researchers suspect Titan hides a deep internal ocean of liquid water mixed with ammonia beneath its frozen shell. If that is true, then Titan holds two different laboratories at once. A surface world shaped by hydrocarbon chemistry, unlike anything on Earth, and a buried ocean where water may still permit more familiar biological possibilities. It is as if the moon contains two separate thought experiments about life, running in parallel across immense time. That is what gives Titan its peculiar emotional pull. It does not simply ask whether life exists elsewhere. It asks whether life must look anything like the version we know. Could metabolism arise in liquids other than water? Could chemistry, given enough patience, invent another path? Or would Titan remain forever on the threshold, rich in ingredients but silent in outcome? To stand before Titan, even in imagination, is to confront the possibility that nature may be more creative than our categories. And if that is true, then the real frontier is not merely finding life. It is learning how many forms of possibility we have been too narrow to see. What if the most familiar place in the sky has been hiding its mystery behind brightness all along? Venus was once imagined as Earth's twin, a neighboring world wrapped in clouds that invited fantasy. From a distance, it still carries that old deception. Similar in size, similar in mass, orbiting close enough to feel almost related. But closeness can mislead. When we finally saw Venus more clearly, it revealed not a second home, but a furnace. Surface temperatures hot enough to melt lead, pressure heavy enough to crush metal. A landscape where any simple hope for life seemed to vanish on contact with reality. And yet the story did not end there. Because between the blazing ground below and the empty space above lies a band of atmosphere where conditions are unexpectedly gentler. High in the clouds, temperatures and pressures become far less extreme, close enough to some environments on Earth that scientists began to ask a question once thought absurd. Not life on Venus, but life in Venusian air. It is a difficult idea, but not an impossible one. On Earth, microbes have survived in clouds, in acidic droplets, in places where sunlight, chemistry, and motion combine in delicate balance. Venus's cloud layers contain sulfuric acid, making them deeply hostile by human standards. But hostility is not the same as impossibility. The atmosphere is dynamic. There is energy. There are chemical disequilibria still not fully understood. And over the years, observations have occasionally stirred debate over whether something in those clouds may be interacting with the environment in ways we have yet to explain. Even if every unusual signal turns out to have a non-biological cause, Venus still forces a valuable shift in perspective. It reminds us that habitability is not always a matter of whole worlds. Sometimes it may exist only in narrow bands, temporary layers, or fragile niches suspended between extremes. A planet can be hellish at the surface and still offer a fleeting refuge above. That may be Venus's most important lesson. Not that life is likely there, but that possibility often survives in the margins. And if we are serious about finding life beyond Earth, we may need to stop asking which worlds resemble home and start asking where. Within even the harshest places, conditions briefly learn how to soften. What if the oldest refuge for life in the solar system is not a moon or a planet, but a giant world's forgotten depths? Jupiter does not invite tenderness. It is immense, turbulent, and unreadable at a glance. A planet made not of ground, but of pressure, storm, and motion. Its clouds roll in bands across the globe, and beneath them, the atmosphere deepens into layers no human being could ever stand upon. For most of history, that very strangeness kept Jupiter outside the conversation about life. It was too large, too violent, too abstract. A place for weather, not biology. But science has a way of widening the frame. In Jupiter's upper atmosphere, there are regions where temperature and pressure briefly pass through ranges less extreme than the crushing depths below. Not comfortable, certainly, but no longer beyond thought. In those middle layers, sunlight is present, chemistry is active, and particles drift in currents that may keep small materials suspended for long periods of time. The notion is speculative, but not without reason. If life can adapt to cloud droplets, shifting chemistry, and unstable environments, then even a gas giant becomes harder to dismiss entirely. The challenge, of course, is permanence. How does anything survive in a world with no solid surface, where downward movement leads to destruction and upward movement offers little shelter? Any hypothetical life there would need to be light enough to remain afloat, resilient enough to endure turbulence, and simple enough to live inside fleeting balances of chemistry and heat. It would not resemble forests, animals, or anything our instincts would name alive at first glance. It might be closer to a process than a creature, a suspended metabolism riding the weather. There is something profoundly unsettling in that possibility. We are accustomed to imagining life rooted somewhere, attached to land, sea, or stone. Jupiter asks whether that attachment is a prejudice of our own biology. Must life belong to a surface, or can it emerge in motion, carried endlessly inside a living sky? Perhaps Jupiter will never yield such evidence. Perhaps its storms are only storms. But even so, the question matters. Because every time we allow life to exist in a form stranger than expected, the universe becomes less a mirror of Earth and more a field of possibilities we are only beginning to deserve. What if the solar system's most overlooked sanctuary is not hidden beneath ice or buried in stone, but wandering between the giant planets in the form of a captured survivor? Callisto rarely receives the same attention as Europa or Enceladus. It does not throw plumes into space. It does not advertise internal heat with dramatic fractures or dazzling brightness. At first glance, it seems almost resigned to silence, its surface so heavily cratered that it resembles a memory of violence preserved without interruption. And yet, that stillness may conceal one of the most durable secrets in the outer solar system. Unlike more obviously active moons, Callisto appears geologically old, even subdued. But measurements have suggested that beneath its battered crust, there may be a salty subsurface ocean, hidden far below the ice and rock. If so, Callisto presents a different model of habitability than the worlds we tend to celebrate. Not a place energized by obvious turmoil, but a place where insulation, chemistry, and immense stretches of time may have quietly protected liquid water from freezing solid. That possibility matters because life does not necessarily require spectacle. On Earth, some of the most resilient ecosystems exist far from sunlight, tucked inside rock pores, deep marine sediments, or isolated aquifers where change comes slowly. A hidden ocean inside Callisto would likely be dark, pressurized, and difficult to stir into the kind of active exchange scientists often associate with biology. Yet the history of science is full of places once dismissed as too static, too remote, too poor in energy, only to later reveal subtle forms of persistence. There is something moving about Callisto precisely because it does not demand belief. It asks for patience. It asks whether we can imagine that the conditions for life may endure not only in dynamic worlds, but also in ancient ones that have simply had enough protection to keep a fragile possibility alive beneath a ruined exterior. If that is true, then Callisto becomes more than a cratered relic. It becomes a lesson in humility. Not every promising world shines with activity. Some may have spent billions of years appearing empty while guarding in silence and darkness the one condition that changes everything: water that never entirely went away. What if the oldest recipe for life is not preserved on a planet at all, but frozen inside a traveler from the beginning of the solar system? Comets have long been treated as symbols of distance and omen, bright intruders that arrive from the dark with a beauty that feels almost theatrical. But behind that spectacle lies something more intimate. These objects are archives. They formed in the earliest age of the solar system and spent billions of years in deep cold, preserving ancient ices, dust, and organic material from a time before Earth had oceans, before Mars was red, before any world we know had fully become itself. That is why comets matter so deeply in the search for life, not because they are likely homes in the usual sense, but because they may carry ingredients and perhaps even temporary habitats that complicate the line between chemistry and biology. When sunlight warms a comet near the inner solar system, frozen compounds awaken. Jets erupt. Molecules locked in ice for ages are released into motion. Spacecraft have found organic compounds in cometary material, including some of the carbon-based building blocks that on Earth belong to the language of life. There is also a more daring possibility. Inside a comet, beneath its crust, radioactive heating or past impacts may at times create short-lived pockets where liquid water can briefly exist. Not stable oceans, not enduring seas, just moments in geological time, hidden chambers where chemistry becomes mobile and reactions can proceed in ways impossible in deep freeze. Such windows may be rare and brief, but life on Earth began under conditions we still only partly understand. It may not take an entire planet to begin asking the question. More important still is what comets may have delivered. Long before life appeared here, worlds were bombarded by countless icy bodies. Some scientists suspect comets and similar objects helped seed early Earth with water and organic molecules, contributing pieces of the chemical inheritance from which biology eventually emerged. In that sense, comets may not simply be potential shelters. They may be couriers of possibility. And so they leave us with one of the most profound reflections in this journey. Perhaps life is not only about where it survives, but how the ingredients of life move through space, waiting for the right world, the right temperature, the right accident, and the right span of time to become memory, metabolism, and meaning. What if the true map of life in our solar system has never been a map of planets and moons at all, but a map of hidden conditions, water, warmth, chemistry, and time, scattered in unexpected places? By now, the pattern is impossible to ignore. A dwarf planet with buried brines, frozen moons concealing oceans, a red planet that remembers rivers, clouds above a hostile world that may briefly soften into something less impossible. Ancient comets carrying the materials of beginnings. None of these places offers certainty. None has yet given us the simple, world-changing proof people have imagined for generations. And yet together, they have already transformed the question. We no longer ask only where life would feel comfortable. We ask where it might persist, where it might begin in darkness, where it might retreat when surfaces become cruel, where chemistry, under pressure, and patience might cross the invisible threshold into the something organized, adaptive, alive. In that shift, the solar system becomes less a hierarchy of major worlds and minor ones, and more a vast collection of experiments, each testing a different version of possibility. That may be the deepest revelation of all. The search for alien life is also a search for humility. It asks us to loosen our attachment to the familiar, to accept that life may not need blue skies, continents, or even sunlight. It may prefer oceans no eye has seen, minerals inside fractured stone, droplets adrift in cloud, or brief moments of habitability in places we once dismissed without a second thought. And still, whatever we find, another truth waits beneath the science. We are searching outward because the question changes us inward. To wonder whether life exists elsewhere is to confront our own fragility, our own rarity, and perhaps our own continuity with everything that endures against the odds. If even the coldest and most distant corners of our neighborhood can hold the conditions for living things, then life may be less a miracle of one world than a quiet tendency of the universe itself. And if that is true, then perhaps the greatest mystery is not whether we are alone, but how long the cosmos has been filled with hidden company, waiting patiently in the dark for us to learn how to see.